Get started here. We're a couple minutes past the top of the hour. So welcome everyone to, I think, the fourth installment of MinneAnalytics Mondays. We appreciate all the engagement coming back week after week and dealing with us ironing through the technical work every single week. So this week we have Greg Hayes, Director of Data Science at Ecolab. Greg spoke at last year's and maybe even the year before, if I recall correctly, MinneAnalytics Data Tech Conference, and was really well reviewed. So I'll be talking MLOps today, and Greg, I'll just go ahead and pass it off to you. And just one quick note. So just like in the previous weeks, if you have any questions, please filter those through the YouTube channel in the comments there, and we'll pass those along for the Q&A section at the end, towards the end of the talk. So Greg, it's all yours.
Very cool. Thanks, Jake. And thanks for having me. As you mentioned, I've been at Ecolab for about the last 3 years, and I've had responsibility during that time for working with R&D engagement and data science initiatives, for having the offshore teams technically report into me. And for the last 2 years, working a lot on trying to solve the challenges of moving data science work from the lab into production, trying to understand what tools, what processes, kind of best practices can be leveraged to help enable this movement. So that's really what this talk is about. It's a journey. We're certainly not done, but anyway, with that said, let's get started. So we're going to start by framing it up a little bit. What is the need? Why is there an interest in MLOps? We'll talk a little bit about Kubeflow, MLRun, and Dask, and give a couple of motivating examples, and then we'll wrap up. So the first question is, what's the problem we're trying to solve? What's the need? These are a couple of comments from companies that study this challenge, this question of how you take MLOps or how you take machine learning products into production. It's pretty clear, I think there's pretty widespread agreement, that the promise of artificial intelligence and machine learning is one that companies are still trying to figure out how to leverage. There's a lot of work that gets done toward developing machine learning projects, models, but in large part, they don't really make their way into production. And the question is, why? And we can think about this problem from a lot of different vantage points, or view it through a lot of different lenses. The one that we're going to look at it through today is that of a portfolio manager. So for those that aren't familiar, portfolio management is kind of a widely adopted practice that large companies use to try and understand and maximize how the investments that they make move from concept to production. And in the idealized state, you can have 3 stages or 4 stages or 5 stages, but in an idealized state, companies want to collect a large number of different ideas. They want to put them into a funnel. And then they want to choose the ones that they think have the greatest opportunity for adding business value. And they'll run some prototypes. And as these prototypes begin to show promise, maybe some will be set to the side. Others will move into development stage. They commit more resources to them. And then eventually you move into some sort of a run and maintain state where these projects become an ongoing part of the business and just operations. And then they get evolved and enhanced over time. So the question is, if we view our data science projects through this lens, then what does it end up looking like, right? What do data science projects look like as part of the enterprise portfolio? And there are a lot of ideas, right? But, and we do a lot of prototypes. As a function across many, many different businesses. But then we hit this choke point in the funnel where things don't make their way through. They just get stuck. And there are a lot of people trying to figure out what's going on here and how we can basically widen that funnel. So let's kind of put our data science hats back on and think about what it takes to get started in a data science project. Well, first you have just the data. Is it available? Is it accessible? Is it secure? Oftentimes those are challenges and roadblocks that need to be addressed. The next step is compute resources. Oftentimes in data science, work gets done in a local compute environment. It's in-memory compute. May be done, on your laptop or in a VM, but provisioning those compute resources for team members can be a challenge. And then once the compute resources are provisioned, how do you enable collaboration? How do you enable security at the user level and at the data level? How do you enable scalability? Frequently we're working with in-memory compute because that's easy and it's fast. But in-memory compute doesn't scale really well beyond, 50 or 60, even 100 gigs of memory. And finally, compute is expensive. So you don't want to, one of the common ways to solve that problem of provisioning compute is we'll spin up a cluster so that we can, work in a distributed compute environment. Well, distributed compute is hard. The lazy compute paradigm is not always intuitive. But then having compute clusters running more or less ad hoc across an organization can get very, very expensive in a hurry. And then finally, we have the question of code. How do you manage your code? How do you persist your code? How do you enable how do you enable collaboration so you can have more than one or two people at a time working on a data science project? All challenges that you have to contend with just to get a project started. Let's take a look at how data science happens today. Typically, it's in small teams. And when we think about a data science project, what we really think about is how do we build the best model possible? We don't really think about the question of how you operationalize that model in general from the outset. Our goal is to iterate quickly with our business partners. We want to develop something that we think is valuable as soon as possible, as quickly as possible. And oftentimes we work in multiple languages. You may see on one team, Python, R, Scala, Julia. There's a kind of a growing interest in Swift, and Google has recently put a lot of efforts toward enabling Swift actually as a first-class machine learning language. And so this is always evolving. I mean, you keep on going. We have MATLAB, we have SAS, the list goes on. Most of our projects have very complex and varied package dependencies. They're difficult to reproduce in a production environment. As we've talked before about this preference for local in-memory compute. And then typically we're doing EDA on static data sets. We're not really working with live data. All of these things enable data science teams to iterate quickly in the prototype stage. So where might this notion of MLOps fit? MLOps meaning how do we take machine learning models and workflows and move them from ideation to operationalization or prototype to operational, where they're contributing business value on an ongoing basis. So we'll posit this idea that, where we start as data scientists is we want to build a model. But of course, from the business point of view, we don't want to build a model. We want to build a data product. And a data product has all of these other things that have to be done. You have to be able to ingest raw data at scale. You have to be able to contextualize that data at scale. You have to be sure that your data meets a certain set of requirements. You have to be able to transform it at scale. You need to do splitting, unit testing, model validation, training at scale, versioning, model release, serving, integration, on and on and on. These are all of the things that are required to move from a model to a product. And the industry agrees that it just takes too long. Typically, if you go and you listen to the Netflixes, the Googles, the Microsofts of the world, they will tell you that usually somewhere between 10 and 12 weeks is what it takes to go from a concept to a prototype model. And that's debatable, but we can use it as a working number. But then model deployment can take as much as a year into production, and it's not sustainable. We need to get to business value faster. So then let's think about how products, data products, are built and maintained? Well, frequently you have a single production grade language that's shared across teams. You don't typically see, for any given segment of a team, multiple languages being used. You converge on a single language for production. Highly reproducible compute environments, that you have to be able to take your compute environment and move it from concept to production, and you have to be able to reproduce it at scale. Deployments are run from source control. Git is the standard today. There have been others in the past, and GitOps has become a very important tool in the deployment process. You typically see adherence to language-specific best practices. People lint their code. There's agreed upon way to write your code, and teams adhere to those. We typically employ, when you're building products at scale, specialized build and release skills. You want to automate this process to reduce variance and improve reproducibility. High levels of unit test and integration testing. You have to be sure that your code does what it's expected to do. There aren't unintended side effects, and that your code integrates with other systems as expected. This kind of ties in closely with automated release and development tools or deployment tools. And then when you think about from a model's point of view, you want to work on live complete data sets, not aged data. And you want it to be connected to source systems, the source of truth. And then you have visibility into product performance and release metrics. So if we think about how companies bridge this gap today between idea and product, today, you typically have this handover or handoff. A model gets built and it's handed over to a software engineering team that then rewrites the model and the data pipelines in an alternative production grade language when your project moves from experimentation to production. It works. It's slow, but it is maintainable, and it ends up with the data science teams being disconnected from product creation and evolution. The alternative path today is to have data science teams automate their own work. It's fast, but these solutions oftentimes then end up being hard to maintain and evolve, and then they miss integration points with other systems and can be difficult to reproduce because of some of the things we've talked about so far. So if we try to look at kind of these two buckets, data science and data products, and we say, well, what tools could be leveraged to take what's kind of the best practices from developing data products and leverage them into data science. So if you look at these specialized skills across build, support, and release cycles, really you're talking about Agile and Scrum tools. And there is a movement to adopt Agile and Scrum in the data science workflow. It needs to be adapted, but it does work. Multiple languages. So data scientists prefer to work in multiple languages, and that's great for prototyping. But when you start moving things into production, when you want to start to evolve them, when you want to start standardizing project structure, when you want to introduce unit testing, you need to move to a common language across teams, at the very least for a given function. It makes it possible for other team members to pick these projects up as they evolve, as they live, after they've been around for a few years, and understand what's been done without having to spend months and months just reading through code. The complex varied package dependencies, containerization technology really opens a lot of opportunities there. So Docker, as an example, there are others, but Docker seems to be the industry standard at this point. Preference for local compute. Leveraging things like infrastructure as code, which Kubernetes has really revolutionized, opens up the opportunity to train models at scale and on demand. We want to be able to conduct our EDA in a scalable environment without having to move code or change languages. And we want to leverage tools that can bridge that distributed to local divide. And we'll talk a little bit about that in just a moment. The specialized build and release skills, we've talked about Git, CI/CD. Those are things that are not commonly used in many data science workflows. I think that the interest is growing. And the more that we can do to leverage things like Git and CI/CD, the better off we'll be as teams, because they facilitate communication and they facilitate the ability to maintain products at scale. And then visibility into product performance and release metrics. We not only want, but we need to be able to see what's happening with our products, because it's well documented that data science models and data products change over time as the data that they are being fed changes. These things are not static, but they're living, breathing products. So, as I mentioned before, there is a recognition that this is a gap, and there are a lot of efforts right now to try and close those gaps. Several projects have been open sourced in an effort to facilitate this. Kubeflow was open sourced a year and a half to 2 years ago by Google, has gained a wide following. MLflow was open sourced by Databricks. Azure MLOps is open source and allows you to leverage Azure machine learning tools to log and version models and to target compute resources. In the last 6 months, 6 to 9 months, I think, Netflix open sourced their data science collaboration platform, which is Metaflow. And then Airflow and Prefect are data science orchestration engines. We also see Saturn Cloud. That's a new one that's come out in the last 6 months. And all of these tools seek to leverage GitOps-based workflows. They're all based on cloud native computing in some form or fashion. They tend to be provider agnostic in general, and the design patterns are emergent, but they're still being discovered. But all of these tools are focused on solving these challenges. How do you move things from concept and prototype to production more quickly? So if we step back and we say, well, what do we need to do? Well, we need to provision a secure, scalable workspace for users. We want to empower users to maintain and create compute environments that are suitable for the work that that's being done. And we want to provide them with the ability to collaborate by sharing and reviewing code with team members. We want to establish patterns, GitOps, for validating code that performs as expected. We want to be able to do unit testing and identify when errors are introduced. We want to be able to provide tools for verifying or linting our code. We want to simplify the migration from production, exploration to production. Integration points between other systems, enable best practices, and remove roadblocks for production. And that's really the focus of today's conversation is about Kubeflow. That's really what Kubeflow is intended to address. It was introduced by Google about 2 years ago. And it's a cloud native computing environment that's dedicated toward deploying machine learning workflows on Kubernetes. If you look at the tools, Kubeflow is the framework, but then all of the tools, many of the tools that you see data science using at scale are integrated into the platform. Kubeflow leverages Kubernetes to create a data science working environment on top of the Jupyter Notebook. We also have Kubeflow pipelines and Kubeflow serving. TensorFlow and scikit-learn are integrated into the platform. PyTorch was recently added. XGBoost is currently in flight. Through the Spark operator, you can run Spark workloads, and Nucleo is part of the project as well. It's a serverless computing framework. All of these are present, available, part of the open source project. And they leverage cloud native computing. The goal is to leverage cloud native computing platforms to scale and enable machine learning. A few tools that we can add to the tool chest to help round out what's missing. Dask is a Python native distributed computing environment that runs on Kubernetes. And it leverages the Python data science ecosystem. Dask does not seek to create its own set of tools or workflows, but it seeks to work on top of tools that Python data scientists that use Python already know. Runs in Kubernetes and can run up to thousands of nodes. It's very lightweight. If you're working in Kubernetes, it takes simply a matter of minutes to spin up a cluster and to tear down a cluster if you're already inside of a Kubernetes environment. It scales down to a single laptop, so you can run this on a single machine as a in-memory compute platform, or you can move it up to distributed. And it's really geared, so if we think about, there's a lot of conversation about where Dask, or how Dask and Spark may be alike, or how they may be dissimilar. Spark really targets a lot of business intelligence, data migration workflows. It's really kind of the MapReduce paradigm. But by virtue of running on top of NumPy and the scientific computational frameworks that are present within Python, Dask enables a lot of very complex computation. MLRun is a relatively new project. It's similar to MLflow, which is open source by Databricks, and it really provides a way to work in a notebook environment, but simplify the process of scaling out. And we'll show a little bit of that here in just a moment. It enables tracking of experiments and monitoring and logging. So if we think about a data science project and its migration its evolution as we go from exploration and ideation to prototyping, to development, and then to this run and maintain stage, what tools from the Kubeflow tool chest might we leverage during that process? Well, in exploration, Jupyter and then Azure DevOps as a sharing, or GitHub as a platform, we can leverage these code repositories to share and maintain our code so that it's protected against loss and versioned by virtue of ongoing commits. But we can work in Jupyter as our local compute environment, gives us our standard notebook that we're all accustomed to working in. As we move into the prototyping stage, then we might want to start thinking about things like what parts of our code should we refactor and migrate out of the Jupyter notebook environment into, in the case of Python, standard.py files. By doing that, it enables experiment tracking, and it also enables us to start writing unit tests. As we kind of migrate our way from left to right across this process, moving from prototyping into development, now we want to start thinking about larger scale data sets. This is where Spark or Dask might come into play. And as these are maturing, we want to start thinking about doing code reviews. When does it make sense for us to start reviewing our work, doing kind of ongoing code reviews, getting other people involved, making sure that we have other eyes on the work that we're doing? Not only does it help us become better data scientists, but it also helps other team members engage in the process as we look to move from prototype to product. Once we're in this development stage, now we should be full scale. We want to have, certainly want to have our automated unit tests, our linting in place. We want to have some code standards available. We want to start working on larger scale data sets. And we may even want to start looking at ways to trigger our pipelines or build out pipelines as we start thinking about the production process. And then once we hit run and maintain, we should certainly be doing things like automated model monitoring and retraining. We should have release pipelines in place so that we can reduce the variance, improve the maintainability of our systems. We didn't talk too much about MLRun, wanted to touch on this just a little bit. MLRun basically allows data scientists and software developers to describe tasks in various environments. So what does that really mean? Well, if we start coding in our notebook editor, this is an environment that we're all familiar with. As their code starts to mature, we start to factor it out into modules that can be imported. And then we can wrap these things in MLRun functions. I'll show an example of this in just a moment. After these are wrapped up in MLRun functions, then we can start to add artifact tracking and logging to a database inside of Kubernetes, and then eventually create our Kubeflow pipelines, because MLRun will return a Kubernetes Kubeflow container operator, which can be then leveraged to build a pipeline. We'll show what that looks like. So I'm going to hop out here for just a second. So this is a Kubeflow notebook. So I'm working inside of Jupyter Hub. And we'll just walk through a little bit. We're not going to execute it in line, but we'll walk through what happens. So we do our standard imports, and we're going to pick up in the process where maybe we're in the development stage. So prior to this, we would be working inside of Kubeflow, inside of our Jupyter notebook. We might do our EDA just like we normally expect. So an import pandas as PD, and a df equals pd.read_csv, so forth and so on. As this project has started to mature, we've decided we're going to factor this out. So so this is one of the .py files. It's been refactored into an importable module. And you can, if you look at it, you can see we've got a function that's load data frame, which is shared across all the functions in the file. We have a start pipeline file, which basically takes in a data frame as either a string or an in-memory data frame, loads it up, does some work on it. Then we can pass that into a trained model file. And the trained model just very simply looks at what's in the index, breaks out a target class variable if it's present, splits it up, does a train test fit, and returns a model. These are all things you might normally do in a Python notebook or Jupyter notebook, but instead we're further into the process. So what might a workflow look like? So we have a database and a project name. We instantiate these as variables in the notebook, and we save an artifact path. This effectively says, hey, we're going to create an artifact that's going to have a unique run ID for every execution, and that's someplace that we're going to save the results of our work for this given run. And we want to start by testing our functions locally. So we import our pipeline, and we also have an exit handler function. MLRun has this notion of a context. So it wants to know something about the space that it's running in. Am I running in a local environment? Are you creating a context? This logs information about my compute location and the resources that are available. And as an example, in the first step in my pipeline, I do a start pipeline. I say, hey, I want to train a model. That's my intent. And I pass it a data frame. This is a Parquet file. And I've added a special variable here called return result equals true, meaning I'm running this in my local notebook. I just want to test it. And I get my Dask data frame back. And I think all of us probably know what this problem is. I have another function. It's a trained model. I also want to return my result. I pass in my context and the data frame that I loaded from the previous step, and I return some performance results from my run. And then I can dump this model out. I can also return a set of scores using a pipeline, make predictions. I have a feature table that I pass in from my prior step. And I can also monitor my model in production. So this is all running in my local notebook, nothing terribly fancy so far. What I can do after that, though, is I can wrap this function up in an MLRun function. So I have, from MLRun, I have this function called new function, and it accepts a path to my file. This is my pipeline.py file that I mentioned before. I specify a container image that I want to run against, and I have a parameter here called kind equals job. This means I'm going to run this function remotely. And I can also mount my local file system. So if I'm running in Kubernetes, Kubernetes has this notion of volume mounts. So I can mount my existing file structure into a container, and I can run all of these remotely. So these become jobs that run in Kubernetes pods. This .run function is what tells me to do that. There are many different runtimes that can be run. So I can run a Dask runtime, I can run a Spark runtime, an MPI, or a Horvad. These are all accessible inside the platform. Basically, and you can customize this, so you can add others as they become available. This is just simply telling Kubernetes, hey, this is where I want you to run this code. What might a Kubeflow pipeline look like after I've done this? So this all looks pretty similar to the previous notebook. I have two functions that I create. These are MLRun functions. And I specify kind equals job. And then I specify a set of arguments that I want to pass into my Kubeflow pipeline. Kubeflow introduces the notion of a domain-specific language, so you can write custom workflows based on this. So that's what this DSL decorator is. I'm using the domain-specific language with a pipeline. I define my pipeline, I pass in my arguments listed above. My pipeline starts by declaring an exit handler. Basically, this says, hey, when this exits, when this when this pipeline ends, do something. In this case, this exit handler sends a notification to a Microsoft Teams channel when the pipeline is done. You could send it elsewhere. You could send it to Slack, or you could send an email. And you could also set it to only send a notification if the pipeline fails. So this enables monitoring. And then I say, with my domain-specific language, exit handler, start my pipeline. And this looks exactly like what was shown in the previous book, in the previous notebook, except I've changed the run function to a .asStep. .asStep is MLRun's way of saying, hey, we're going to run this as a container operator inside of Kubeflow. I pass in a set of parameters that are the same parameters that my function takes, and I specify an output, which is a value or values that can be passed between steps in a Kubeflow pipeline. And then I specify a condition. If I want my pipeline to train a model, I can pass in, I can output or emit from my start pipeline step an intent value of train, and the steps of loading the data frame or loading a file, training a model, making a set of predictions, and then returning the results of that model back for logging would occur. If instead I pass a predict intent, I would simply load a data frame, load the last trained model from my database, my MLRun database in this case, and return a set of predictions. Or I can have another step that says monitor, pipeline intent equals monitor, in which case I will make a set of predictions and return a set of metrics for monitoring the model in production. Finally, this is where Nucleo comes into play. I define a handler function. The handler function is a Nucleo function that accepts a JSON object and runs the pipeline specified above, depending upon what arguments are passed. So what might this look like? So here I have a Nucleo generator function. It takes a spec, and I want to test to see whether my Nucleo function returns an HTTP response. I just want to test if the endpoint's active. This pings my Nucleo function from above. Here I pass it a request equals test. And in my Kubeflow pipeline, I have a JSON object that says, hey, this is, if I receive a request equals test, return a body, this is an test endpoint for the Iguazio platform. And you can see this is what I got back when I executed that cell, which is Kubeflow. I can return a predict, and I will generate a run link. I can run train and I can run model. And if we flip over, these have now been kicked off. and I will dynamically, based on the JSON request value that was passed, I will dynamically either train a model and make a set of predictions. Well, this is actually returning a set of predictions. I will train a model, make a set of predictions on that trained data set, and return a set of model metrics. Oh, that's the wrong one. And I also have the option to just monitor that model in production. And you can see that these have taken off and started running. So that's what a Kubeflow pipeline looks like. I also have a little bit of an example, a couple of slides here to talk about Dask and where Dask fits into the workflow, because these are all still in-memory problems. And I looked for a motivating example. I found one listed here. It's a Kaggle competition where it was written in French, but the user developed a concept workflow using data set from 2015. It was flight delays and cancellations. The data set that he used as an example was 500 megabytes on disk. And when the user developed his workflow, he built a model for the month of January in 2015, trained his model on data from the first 3 weeks of the month, and then tested his model against the final month. And I wanted to see how closely I could replicate that, but using a slightly larger data set. And just looking through his exact code, he actually selected 1,800 rows on which to train his model and then test against 1,200 rows. Simple linear regression. I found a similar data set. This was on Amazon Web Services open data sets. It's all flight delays and cancellations from 1987 to 2008. That data set is 70 gigs in memory. And I selected 5% of the data for exploration on all years and built a Dask cluster. It was 20 gigs of memory, 5 workers, and effectively tried to replicate the data pipeline that was described here to see what would happen if I tried to apply that pipeline and this alternative Dask-driven pipeline to subsets of these larger data sets. I trained a linear model, and the linear model that the user reported on Kaggle, he scored 53.1 minutes MSE, mean squared error, on the data set that he used. This was obviously, it was a different data set and parsed differently. When I ran his exact code on my local machine, 16 megs of memory, I was able to get a mean squared error of 175 minutes and 199.9 on the test data set. But there were some interesting things because I wasn't able to actually use the data as written, the code as written on my data set. Not sure if this is rendering large enough.
It's coming through all right.
It's coming through, okay,
Yeah.
all right. So a couple of comments here. I just wanted to do a bit of a side-by-side comparison between the code that the user posted and how it was modified to execute. And kind of the most important part of this slide on the pandas data cleaning side, side of the slide, is the last 3 lines of code. So here he defines a number of functions and creates new columns based on those functions using an apply operation. So one of the things we know from a data engineering point of view is that apply is a row-wise operation, which is non-ideal when we talk about scalability. So effectively, that was all rewritten to be vectorized operations. So rather than iterating through every row when we create a new column, we go through and we operate on all the rows to the best of our ability. And we take the execution time of these steps from 20 minutes down to less than 2. on something like 1.5 gigs of data. Another comment about scaling up. So trying to use the data as provided, we took 5% of our 70 gig data set, and they have two functions, get stats, which is called in an apply operation, and several apply operations inside of this get flight delays function. Again, these are row-wise operations. When this set of code is operated against 1 gig of data in memory, we end up with about 40 minutes of execution time, and we are unable to actually train the model. It fails without memory errors when run on a 16 gig machine in memory. We moved to vectorized operations on Dask. Dask operates in partitions, so Dask is a collection of pandas data frames. And we eliminate those long-running apply operations, move to vectorized operations, and we also take out the apply call to get stats, and just to convert it into a standard aggregation on a group by, which returns column attributes or column statistics natively. That reduces our execution time from 20 minutes down to 4 minutes, and we train a linear model in approximately 5 minutes. Okay, so final thoughts here. And I guess maybe before I start the final thoughts, if we wanted to take that model on Dask and scale it up using an MLRun step on Kubeflow, what we would do is we would declare our kind as a Dask operator, and it would just run that natively in a remote environment on Dask. So now final thoughts. When we talk about data science at scale as part of a enterprise portfolio, what we're really thinking about is how do we create data products? And in today's world, oftentimes we start with this question of how do we create a model? How do we create the best model we possibly can? But if we view our challenge through the lens of building data products, not just creating models, we have to think about all these other challenges. And the sooner in the process we can begin to think about and tackle those questions and these challenges, bring them into part of our workflow, the faster we will be able to move from ideation to prototype, and then remove that bottleneck and get our products kind of on out into the wild, where they can add business value, become an ongoing part of our operational model. And that is all that I had.
All right, great. So it doesn't look like we got any questions through the YouTube, but I've got a few here myself. So, you know, when thinking about how have you applied this, you know, within Ecolab and your team, how have you been enabling this type of framework for, I guess, the data scientist who would identify as more of a statistician than a programmer? And I'll just leave it at that.
Okay. So fundamentally, for any given user within our workspace, within Kubeflow, so forget Ecolab's workspace, any given user can create, or for any given user, you can create a pod that has any of the tools that they may be comfortable working in. So, and in the Kubeflow open source project, you can provision those, you can request compute resources from the pod, or from Kubernetes for that pod. So if I wanted to have, let's say Python as an example. So let's say as a Python user, you wanted to work in stats models. You know, we could provision a pod with as many compute resources as you might want, be granted from the cluster, whether it's 4 cores and 16 gigs or 4 cores and 64 gigs of memory, and then give the user the tools so they have access to the pod. They can install any packages that they want. And you have the ability to run other languages as well. It's just Python is a kind of a first-class citizen in that framework. So I guess my question back to you might be, are you thinking more about R versus Python, or are you thinking about different kinds of packages that as someone who identifies more as a statistician might want to use?
Yeah, I guess I'm thinking of the potential notebook hell that we can, often find. It's like you mentioned, right? You talked about the process of kind of culling code from a notebook and determining. I mean, could you speak a little more to that? The process of looking at, data scientists X, Y, and Z's notebooks. They're working on different models, but determining what parts of those notebooks should maybe go into a core, kind of a central competency core repository for use across the broader team to kind of help this pipeline, this whole framework, be more repeatable and useful in the future.
Yeah, so there are two pieces to that, I think. One is, how do you build common components that can be used by multiple team members? And then the other piece of that challenge is, how do you take code that is, as you said, you write a lot of code, much of it's throwaway. It doesn't end up needing to be used any further, right? So it's important for data scientists and data engineers to identify the code that they want to leverage, that needs to be leveraged as we think about scaling up, and effectively refactor that code out of the notebook into importable modules. As long as that code lives in a notebook, it can't be tested. It's difficult to find and identify what's important. So users have to be able to say, okay, right, we've decided that this is the framework or the specific snippets of code that we want to use going forward, right? Let's refactor this. Let's apply some unit tests to it. And when it gets integrated into, when we do a git push, we automatically test that code so that we know that it does what's expected. So that's one piece. The second piece is, how do you build components that can be leveraged by multiple team members? And the MLRun library enables a fair bit of functionality there, where you can actually import an MLRun function directly from a Git repository. So if I have a centralized Git repository and I write one function that, let's say, imports code from AWS, that function can then be downloaded and used by all of the different team members if I put it in Git. And it's simply a matter of specifying that you want to import a function and where that function, what Git repository that function is located in. So I think there are two pieces to your question.
Great. And we did end up getting a few questions. We got about 10 minutes left here, so plenty of time. So we got a couple questions from the YouTube here. I'm going to try to condense them. So, one is how large of a team do you have? And then expanding on that, talking more specifically about how this, data science development and operationalization has reduced that the life cycle. Has it been a reduction from 6 months to like 3 weeks? And then in that same vein, are you able to feed more, or has your capacity for projects also increased? Are you able to field 3 to 4, more projects as you did previously? It's a lot there, but.
Okay. Well, I guess I'll address the question on the teams first. So in terms of the team, there are actually, there's one team within Ecolab, and we have approximately 20 offshore team members, 15 to 20 offshore team members. And then we have another, let's say 10 to 15 inside of North America. So fairly large team. The whole team does not report to me. It's primarily the offshore team that reports to me, as well as some anchor functionality. So kind of geared towards research and development. To the question of life cycle, so we're pretty new in this process. We've been working with Kubeflow for, in some form or fashion, for about the last 9 months. And so we're really on this, it's, as we said, towards MLOps. It's a journey for us. One of the first challenges we were trying to identify is, how can we more quickly, more easily provision compute environments that are secure for our team members to utilize and also to scale. So if you look at Kubeflow, kind of our first look at Kubeflow, it was, how do we go from, we're going to work in a local compute environment where we're constrained to the memory that we have available to us, to, someone on the team needs 50 gigs of memory, right? How do we provision that for them without having to go through a lot of hoops and hurdles? Well, if we have a Kubernetes cluster that is deployed inside of a network, and then they can simply log into that cluster and request it. We have Docker images that have been built that have certain sets of packages and available to them. And they can say, hey, I want that Docker image and I want this much memory and this many cores, and they could just start, which really simplified the process for us. It also enabled us to much more quickly provision new users and maximize the compute utilization that we had. Because if we have a cluster that has so many nodes and so much total memory and so many total cores available, then you don't have to worry about going above and beyond what you've allocated, as opposed to having individual users spinning up clusters ad hoc. Then that becomes a kind of a whole nother set of challenges to manage.
Sure, great. All right, so we got about 5 minutes left here. I don't think we have any more questions coming through. So do you have any final parting words, Greg?
I guess my only comments are, as we think about this, how do you meet the challenge of moving projects from concept to production? As we want to add more business value and become a more integral part of our business performance, we have to accelerate this process. Kubeflow might not be the end all be all. There are several projects out there that are seeking to tackle this. It's a recognized challenge, but any way that users can find to accelerate that process can do nothing but enhance their contribution to the business. Great.
Yeah, that's a great summary. So thanks again, Greg. Always, we love having you back. One of our better speakers, always very thought-provoking. So with that, we'll wrap up. Again, thanks everyone for attending. Thanks again to Greg. And then next week, next Monday, in a continuation of these MinneAnalytics Mondays, we'll have Rami Crispin talking about the COVID-19 R package, kind of taking the idea of tidy data and applying it to the myriad COVID data that's out there. So that ought to be really interesting and certainly relevant. So we'll look forward to seeing you all again next week. Thank you.